All right, morning, everybody. We'll go ahead and get started. No, it's a busy week. I just learned it's a busy week, 2 midterms for those taking heterocycles and organometallics. So just want to start out going through some administrative details. The first and most pressing being that we have our midterm coming up on Thursday. Same time, same place. Reminder that you'll be allowed 2 hours for that midterm. The intention is that it takes 90 minutes, give or take. It's not really meant to be severe time pressure. So it'll be 2 hours. We'll bring in some bagels. So you have some, between the 3 of us, we'll bring in some bagels. So you have some brain food to power through. And in terms of coverage, today we're supposed to get through, according to the syllabus, supposed to get through carbonylation. We probably won't do more than just scratch the surface there. So the focus will be on through hydrogenation if you're trying to organize your studying. Although, I mean, honestly, at this point, I think you should, with the tools that we've been building and developing, you should be able to look at any catalytic system and have a pretty good idea of what's going on. And so if you might encounter things that are a little bit outside of the strict coverage, and that's the nature of any graduate course here at Scripps. There was an adjustment. I think when I put together the original version of the syllabus, didn't realize that we're going to have so many overlapping deadlines and events all this week. So we pushed back the due date, and I guess that's not reflected here in this version of the syllabus, but I'll update that. And then we'll upload a revised version. So the Wikipedia project draft deadline is now, as you saw in Annabelle's email, the 20th at midnight. So I think when we were just looking at the calendar and seeing what was going on in heterocycles too, we thought it was just too much going on this week. So we pushed that back. If you have any questions about that as you start putting it together, we're always here for you. And if you have questions about organization, how to go about structuring your article, I would direct you to on our lab website in the resources tab. Each year we have some of the ones that were voted top article of the year. And so those are good places to start just in terms of formatting and organization. Any administrative points I haven't covered from the TAs? We're good to go? Okay. Yeah, the midterm is written. We've reviewed it all together. So I think I'll say the same thing that I feel like I say every year, is that use good test taking practices, by which I mean take some time at the beginning to look through the entire exam and see what topics are covered when and where, and prioritize your time accordingly. There will be points to be had up and down the exam, so don't perseverate on things that might be you might find a little tricky. Move on and come back. And then reminder to be familiar with your periodic table, not only because that's the first question, but I think it would just save you so much time to just be able to get through that very quickly than have to think about it. So please, in the intervening 2 days, pop that up on your phone when you're walking to and from your car, and refresh your memory on that. Okay, questions, Sebastian?
Just to confirm, it's the first 3 rows. We don't have to do the
First 3 rows. No actinides, no actinides. Any other questions? All right, if not, let's jump in. Let me just hook up my. So we're now well on our way in terms of catalysis, and we'll cover some of the most historically and widely deployed homogeneous catalytic reactions that have been developed, starting with hydrogenation. And one of the points that's interesting to reflect on is that until about the 1960s, it remained an open question about whether any type of catalytic homogeneous process could rival what had already been observed and developed in the realm of heterogeneous catalysis and even biocatalysis. We're familiar in the context of hydrogenation, many of us, including even your humble instructor, have run heterogeneous hydrogenation reactions before. Typically, these are the active catalyst is some type of nanoparticulate, palladium or platinum on a solid support. So these are things like mesoporous carbon, for example. And these work extremely well, but what they lack is tunability and clear-cut rationalization of mechanisms, some of the same virtues that have motivated homogeneous catalysis in general. And so by virtue of pivoting to homogeneous catalysis, building up a mechanistic understanding of how these reactions take place, that has ultimately been key in developing asymmetric variants that were awarded a Nobel Prize now a couple decades ago. So we'll have the major focus be on homogeneous processes today, but I think we all appreciate that heterogeneous hydrogenation is highly useful and is a complementary technique that's a field in and of itself. And nestled in here within this lecture on hydrogenation, we'll talk about related processes called transfer hydrogenation, which is particularly useful for carbonyl compound hydrogenation. And they share some of the common mechanistic features, but have some differences between classical and transfer, so we'll try to unpack that. In terms of general mechanisms and terminology, there are two pathways to guide us here. The first being a hydride, so-called hydride mechanism, where a low valent metal is initially engaging with H2 to form key dihydride intermediate that then reacts with the olefin. And then the olefin mechanism is effectively the opposite sequence of events. And why there's some importance in distinguishing between these two pathways is that in the early development of this field of homogeneous hydrogenation, the operative mechanism and what mechanism was operative played an important role in motivating the development of different catalyst architectures. I'll take a minute here to just go on a brief tangent. It's not really that much of a tangent. I guess it's quite related. But I want to remind everyone of a point that we've covered briefly up until this point, which is that metal hydride intermediates have this interesting set of properties that, depending on the nature of the metal, depending on the nature of the ligand, depending on that metal's oxidation state, the metal hydride can be hydridic, reacting with patterns that are familiar and similar to things like borohydrides, main group element hydrides. Or in the opposite extreme, metal hydrides can exhibit protic character and react like mineral acids. And then along kind of an orthogonal axis, depending on the metal involved, this is particularly important for first row metals, where the metal hydrogen bond is especially weak. It can act like hydrogen atoms. So this is a continuum of reactivity. And it's not always clear cut that you're in one mode or the other. One way that has been one experimental technique that has been used to tease out the reactivity profile of metal hydride as developed by our very own Jin-Kuan Yu during his time working with Joe Spencer at Cambridge, and this is known as the Spencer U test, where in situ generated metal hydrides can react here typically under low H2 equivalents or conditions under which you will not get exhaustive hydrogenation, just enough to initiate the reaction. Then you can use polarized Z-configured alkenes, and these won't undergo the full hydrogenation process. They'll only initiate and then undergo an isomerization. And where the, if you use D2 gas or some deuteride equivalent, you can track down where the deuterium goes, and that can allow you to pin down the polarization of the metal hydride. So for example, in the case of a metal H that is hydridic and has strong delta minus character, you would imagine this would react at the delta plus H initially. Let me draw this as deuterium so it's more clear how this actually works. And then in a metal hydride that's polarized in the opposite way, you can imagine this would prefer to react with opposite regioselectivity here. Thinking. Let me just use a different coloring scheme here. So this is a powerful strategy for, from a reactivity perspective, not a structural perspective, reactivity profiling perspective, we can get a sense of the preferential reactivity. And this has been used in this initial study was used to pin down reactivity differences between palladium hydrides and rhodium hydrides. Yes, Eugene.
Wait, so is this, I'm confused what this is supposed to try to tell you, like the polarization of the metal hydride bond or the polarization of olefin?
The polarization of the olefin is known based on our physical organic framework. So it's a readout for the polarization of the metal hydride / metal deuteride.
What does that like tell you about the bond?
What does that tell you? So in an extreme where you have, but let's just consider the top substrate. So if you have a metal deuteride that's highly hydridic, you'll see deuterium incorporation at the beta position. If you have a metal deuteride that's highly protic, the deuterium would go to the delta minus position. So in the product, you can read out what you will see is, let's say in the purple case, you would just see deuterium here. Each here. And you could say, okay, the deuterium's only get incorporated at the alpha position. This is a more protic metal hydride / metal deuteride. And the key point here too is you're not running it under forcing enough conditions to get exhaustive isomerization or exhaustive hydrogenation just to initiate the isomerization. If it would exhaustively hydrogenate, then it's harder to get a clean interpretation of the data. So it goes through an intermediate that's common. So let's play out this case, for example. So this is crystal clear. This intermediate In addition, then you're gonna have a just add it in. Resolution that will eventually lose. Does that make sense?
Yeah.
Any questions on that? Okay, let's take a peek at problem of the day number 1 from the day 10 worksheet, and we've given away part of it already. So we're going to take a look at Wilkinson's catalyst, developed in the 1960s, historically important. We've encountered it several times in class, good one to just commit to memory. So now we're going to put on our thinking hats and look at retrosynthetic logic as applied to preparative organometallic chemistry. So let's first, maybe we'll do these in opposite order. So let's consider 2 different routes to make Wilkinson's catalyst, the first starting from rhodium-3, the second starting from rhodium-1. So what do you like here from the for rhodium-3 approach? Al, what do you think?
I guess you can start either from cationic tetrachloride, if that's available, or rhodium trichloride if you want rhodium-3.
All right, so your first question, the first question to encounter, sorry, I realized I didn't get my notes out, is what oxidation state, or what are the common rhodium-3 precursors? So in general, just to orient ourselves when we're thinking about preparative organometallic chemistry, the oxidation state of the metal that we dig out of the ground is the oxidation state that is going to be consistent with the oxidation potential of O2, right? And so the stable form in an aerobic environment of a given metal salt will be what we can get to via O2 oxidation. In this case, it'll be rhodium-3. And so what are the common rhodium-3 progenitors? And what did you say there, Al?
I was thinking either a cationic tetrachloride or a neutral trichloride.
Okay, let's do a neutral trichloride route, and this is available in its hydrate form. And then what do you like here in terms of reactants?
You can add excess triphenylphosphine
Okay, y-axis.
so that you can ligate with 3 ligands, and then it can also act as a reducing agent.
Ah, perfect, okay. So it's acting as a reducing agent, so what is it ultimately going to get converted to?
The triphenylphosphine dichloride, phosphorus 5.
The dichloride will be dichloride, which then will eventually get to the triphenylphosphine oxide, yeah. Is that what you had in mind, Al?
Yes.
Okay. Any questions on that for Al? fairly common strategy when you have a readily available, inexpensive ligand like triphenylphosphine. You can just use it in excess and it's playing two roles, reductant of a higher valent, higher oxidation state metal and as ligand. But the next strategy will be more applicable if you're using ligands besides triphenylphosphine, perhaps more designer ligands that you don't want to burn through and use as sacrificial reductant. Any thoughts on this? So as a general strategy, we just want some ligand that's probably going to be L-type that is readily displaceable, that's going to give clean ligand exchange. And the one that fits the bill here will be this ethylene complex. It's a dimeric complex. And then we can just nicely put however many equivalents we want of our tri-organophosphine. This can be triaryl or trialkyl or aryl alkyl mix. That's the nice advantage of this strategy. So the advantage of this is that there's more breadth of ligands. The disadvantage is you need to get your hands on this rhodium-1 precursor, which you have to make likely from the rhodium-3 precursor. So it's going to cost you something in steps, but give you something in terms of modularity. Okay, let's talk about reactivity profile in the context of homogeneous hydrogenation of the Wilkinson catalyst. So this is straight out of the Hartwig textbook. Sterics play a really important role. In general, terminal olefins are more reactive than the various flavors of internal olefins. There's an exception in the case of cyclic. And I think the role of sterics can be appreciated by zeroing in on the relative reactivities of Z versus E olefins. And we see this in our own labs research, that there's often huge differences between Z-configured olefins and E-configured olefins. So these are 50-fold kinetic reactivity differences here. And then tetrasubstituted olefins are generally outside of the realm, even the cyclic form of things that can be reduced by Wilkinson's catalyst. The reaction is cis selective, or perhaps more accurately, cis stereospecific or syn stereospecific. This initial syn stereo specificity can be eroded over time, and that's why we would describe it a little bit less precisely as cis selective through secondary processes. And then the reason this caught on as a preparative tool is that it can proceed at ambient pressure and temperature. Okay, this reaction proceeds via a classical hydride mechanism. So let's go ahead and see that in action. So let's take a look here at this starting point. Amy, do you want to help with the quick electron count?
Yes,
Here.
sorry. Wait, sorry. Can you, oh, that's just like looking
Up
at
the
the
start.
starting point.
Yeah.
Yes, so it's rhodium-1, so you have it's D8. And then you have 4 ligands, so each give 2 electrons. So yeah, 16.
16 electrons. Okay, so that's good because it gives us one possibility. The simplest possibility is that H2 just binds. It's a 16 electron complex after all. So it can coordinate H2 through what would be an associative mechanism and then undergo oxidative addition to get us to what's our oxidation state and electron count here? Now, Amy?
The oxidation state is rhodium 3,
3,
6, plus 2 more, you're still 18.
18 electrons. Beautiful. So that's certainly one possibility. The other possibility is that we lose an equivalent of triphenylphosphine. And in that case, the math here is pretty easy. We haven't changed oxidation state. We've just lost one ligand. So we're going to get to a much more kinetically reactive 3-coordinate 14 electron complex, which can also undergo oxidative addition to get a dihydride, but now a 5-coordinate 16 electron dihydride. We mentioned before that in the oxidative addition and reductive elimination elementary step modules, that these odd coordination number intermediates are highly kinetically reactive due to the underlying geometries and the orbitals at play. And so it turns out both pathways are competent. This bottom pathway is the one that is responsible for the lion's share of the reactivity.
Why would it do that though? A lot less stable.
What's that?
Why would it do that if it's a lot less stable? Is it just, it forms a very small amount of it and then immediately reacts?
So if you monitor that, yeah, I think that's one way to, I think you hit the nail on the head there, Oliver, which is that this is a kinetics versus thermodynamics thing. So if you monitor this reaction by solution state NMR, you'll see that it sits at this dihydride 18 electron complex, and that might suggest to you that this top pathway is preferred, but actually this is a classic kinetics versus thermodynamics situation. So the lowest barrier pathway, the lowest potential energy barrier for the system to traverse is to lose a ligand, get to the reactive 14 electron complex, slide over, undergo oxidative addition to make the, so go from 14 to 16 electron, coordinate an olefin. What's nice about this 16 electron form is you have a built-in open coordination site that can then bind your olefin, undergo 1,2 migratory insertion, and then it's a series of familiar steps, hydrometallation, CH reductive elimination. The difference here that Oliver is asking is quite dramatic. So it turns out between pathways 1 and 2, there's a 1,000-fold rate difference. We've talked about some of the underlying reasons for that. Okay, any questions on Wilkinson's? We'll see more examples that reinforce some of these themes moving forward, but we'll now cover another class of historically important homogeneous hydrogenation catalysts. These are the Schrock-Osborn catalysts. So are tracking closely the timelines here. You'll notice an interesting little fun fact. The first report on Wilkinson's catalyst happened in the mid-60s. Schrock-Osborn family of catalysts picks up in the late 60s. And Osborn was a former, well, at the time was a current and then became a former trainee of Wilkinson's. And so you can then get an appreciation for the fact that as a student with Wilkinson, he got a firsthand glimpse of the limitations of the Wilkinson system and was motivated in his own career to develop a new generation of catalysts to address them. Yes, Rico.
Right, I don't know what the answer is, I don't want to answer it, but can we go over problem up to day 1B before we go to problem 2?
Sure.
Yeah, about the iridium based. Why is it less reactive?
Oh, thanks for, yeah, thank you for bringing that to my attention. So problem of the day. 1B, thanks for reminding me, Riku, was rationalize why the iridium analog of Wilkinson's also studied so we'll call this the Wilkinson star catalyst. Although it's not a star from a reactivity perspective, why this catalyst is much, much less reactive. So since you asked it, Riku, you knew I would call on you for your thoughts. So what do you think here?
Is this something about my guess? Sorry, I don't have any good basis for it. Is it the first ligand dissociation to the 14 complex much slower for the iridium?
Why would it be slower?
That it's the iridium phosphine bond stronger because
I think you got it. You did all the hard work.
yeah.
So what do we know? We've got second row, everything else is the same. We're just comparing second row, third row. When we go second to third row, what do we know about the third row? The orbitals involved are more diffuse. It's softer. Is phosphine a hard ligand or soft ligand? We'd say it's a soft ligand. So it forms very strong bonding interactions with ligands that have themselves diffuse orbitals. So that strength of phosphine metal bond will be stronger. Ligand dissociation to get onto the fast cycle will be much slower, and you'll have worse kinetic reactivity. Pierre, did you have a thought?
You also view it as greater electronegativity of iridium and that reason being why it's harder to dissociate and become a 14 electron complex. I guess my question is, even with other ligands beside phosphine ligands, maybe things that don't have the same hard soft acid base interactions with each other, is it also the case that the 14 electron complex is prohibitively difficult to access on iridium?
Well, okay, let me maybe circle back so we'll cover Crabtree's catalyst, which is a prominent iridium homogeneous hydrogenation catalyst, and we can it's interesting to compare and contrast between that and Wilkinson's catalyst, and I think it will give you some hints about what some of the structural requirements are to have really fast reactivity with iridium. And I think the name of the game you'll see there is weakly coordinating ligands that can fly off. Does that answer your question? Yeah. All right, so we said I did a brief scientific, thanks for reminding me about that, Riku. Scientific genealogy to give you a flavor for where the origin of some of these ideas comes from. Wilkinson begot Osborne begot Schrock, and some of the giants in the field of homogeneous catalysis. Key design features of the Schrock-Osborne family of catalysts, there's typically a non-conjugated diene ligand. You'll see that can be cod, it can be norbornadiene. And we'll talk in a moment about what happens to that ligand, what the fate of that ligand is to get on cycle. There's then most commonly a bisphosphine. It can be two equivalents of monophosphine as well. And a key point is that it's cationic. And to ensure that it is cationic, it's typically in association with a weakly coordinating counteranion, think BF4, PF6, et cetera. So here's a example of what we're looking at when we're talking about Schrock-Osborne catalysts. Okay, let's see how these things get on cycle. Let's do the same analysis that we started with last time. So Clara, what do you think here? Let's just do a quick electron count for this so we can at least get a sense of what steps it is capable of.
So, it's +1 oxidation state.
Okay, how'd you get that?
1.
Okay, only neutral donor ligands, overall +1 charge. The +1 has to come from somewhere. It comes from rhodium. That gives us then 8.
8 electrons. And then you have 8 electrons from the ligands.
Beautiful. Okay, so we've got some options. We could dissociate a ligand like we did in the Wilkinson case, but that might not be what we want to do here. Why would you think dissociation of this particular ligand drawn with the bisphosphine could be slower?
Can come back, it's bidentate.
There we go. All the ligands are bidentate, so initial, we learned that in one of the first lectures that chelation gives you something like 5 orders of magnitude on the thermodynamic side. So it's going to be less favorable here. So, all right, back to Clara. So what can happen instead then?
So then, I guess no ligand falls off, so there's no dissociation.
Okay.
Association.
All right, so we're gonna get our H2, we're gonna make our sigma complex. We got a little bit overlapping there. Okay, and then what do you like happening next?
One of them fighting.
One of what coordinate? Hydrogen, okay, so I think you got it. So we formed the sigma complex. And then you said coordinate, but I think you may have meant oxidative addition. With dihydride, now you're up at rhodium 3. And then what can happen next?
One of the bidentate ligands.
So now you've got this situation, you've got hydride ligands and you've got olefin ligands. And so you could, in previous problems we've covered, when you've got a hydride and you've got an olefin, that's a recipe for what elementary step?
Productive elimination.
It will be, you're right, but you're a little ahead of the game. So we will have a sequence of migratory insertion, AKA hydrometallation, hydrorodation, and then CH productive elimination. And then we will do that 2 cycles through. So in the end, we will lose cyclooctane. And if we want, we can draw out the H's so we knew where the double bonds were. And now we've got a hot to trot Salvato, rhodium 1, bisphosphine, ready to rock and roll. Questions
You
on
have
that?
to
Yeah.
hydrogenate both sides to dissociate the ligand, or will making it monodentate already?
That's a good question. I think because those olefins are strained, they will be the first to go in a hydrogenation. But your specific question was a good one, which is like, what's the minimal point at which it can be catalytically active? I think it would just depend on what you're hydrogenating. So if you're hydrogenating something that's equally strained and you're hydrogenating norbornene or something, then you can probably do that with while retaining the cyclooctene, but maybe not if it's something less strained. It's a thoughtful question for sure. Okay, so reactivity. Empirically, it's been found that the bidentate Schrock-Osborne are more reactive and presumably also more stable than their monodentate counterparts. So when you see these drawn out, they're typically drawn as the monodentates because those are the most widely used. The importance of the reaction being the complex being cationic is critical. That increases their affinity for olefins and is key to their catalytic success. We talked about the dual nature of metal hydrides being protic or hydridic. And so these metal hydrides have protic character. And so in the presence, if you can imagine, if you do this thought experiment where you run the reaction in the presence of base, then you can get yourself into trouble, because if you have a protic metal hydride, you can deprotonate that metal hydride and get to a less reactive monohydride intermediate. So to counteract that, these reactions are often run with an acid additive.
But can you repeat that one more time? Why do you need an acid additive?
To avoid deprotonation of the rhodium dihydride intermediate that has protic metal hydride character. Is that clear, Riku? So this is the active form as we just saw up here, and S just means solvent. And so this was the question you asked, Riku, which is that acidic, oh, this needs to be, let's see, this intermediate resultant. Sorry. This doesn't make sense to draw like this. Okay, so in terms of mechanistic details, I won't say too much about this other than to say that these are the canonical olefin mechanisms. So one mnemonic that I like to remember is that when you're in the rhodium realm, if the complex has an olefin in the starting material and the pre-catalyst, it's likely an olefin mechanism. Has an olefin mechanism. If it doesn't have an olefin, it's a hydride mechanism. So that's the key comparison of the Wilkinson versus Schrock-Osborne. So they coordinate olefins first. And again, it's like, that's exactly what we saw in the catalyst initiation process. It's got a diene on it, and then it still can react with H2 to get on cycle. Okay, now we're going to turn to our chemist of the day from the day 10 worksheet, who kind of given away the goods here. This is Bob Crabtree of Yale University, educated at in the UK with some of the giants, Joe Chat and Malcolm Green, and then trained as a postdoc in France before he spent his entire academic career at Yale. And among his many contributions are studies of hydrogenation and CH activation with well-defined iridium complexes. So, for some of the historical accounts of this, I would draw everyone's attention to this review from Crabtree himself. He's a very lucid and vibrant writer, and so it's really interesting to hear his accounts of his own group's research. So this is the structure of Crabtree's catalyst, and here we can get a sense of the answer to Pierre's question about what are the design principles required to make an active iridium-1 complex. And you'll see one of the big changes is that instead of this bisphosphine architecture, we've swapped out one of the phosphines for a much more weakly coordinating pyridine. Pyridine will be especially weakly coordinating given that we're with a third row metal here and you've got a soft hard mismatch. So it's cationic and you swapped out one of the phosphines for pyridine, so it's kinetically activated in that sense. It's an orange to yellow complex. If you dissolve it up in solution and treat with H2, you get a new complex. Anybody want to take a quick stab? Hopefully obvious by this point in the lecture. Just going into dihydride. Just going to draw these generic L. Oops. And interesting here that this complex, at least under the operating conditions of this experiment, you don't observe hydride insertion or reductive elimination, perhaps because the bonds that are involved are stronger given that you're a third row metal. A key point that Crabtree emphasizes in this review is that the Crabtree catalyst works best with non-coordinating solvents, DCM, chloroform, and actually performs very badly with some of the classical coordinating solvents that were used in the Schrock-Osborne, Wilkinson catalytic systems. And so in the early days, they thought they had a real dud on their hand because they did head-to-head comparisons with some of the classical hydrogenation catalysts that were developed in the 60s and found that it was no good. Only when they switched to non-coordinating solvents did they see reactivity turn on. And again, I think that this gets to the point that Pierre raised, which is that you have a cationic, highly activated iridium complex with weakly coordinating ligands. So coordinating solvents are especially inhibiting for this type of system. And the key point for practitioners is that this is the most active homogeneous hydrogenation catalyst known. I mean, there could be some that match it or surpass it in some contexts. But if you wanted to push a hydrogenation to its theoretical limit, at least a homogeneous hydrogenation, you run this, and then you can convince yourself that it can't be done. So what do we mean when we say that? This Crabtree's catalyst can even hydrogenate some of the most challenging pebble bonds, like tetrasubstituted olefins, for example. Mechanism here is more complex, and there's evidence, if you dig into the literature, for both hydride and olefin mechanisms being possible, with the lion's share of evidence pointing to the hydride pathway as the most important for catalysis. Okay, let's take a look now at problem of the day number 3, which is one of these examples of a tetra substituted olefin hydrogenation, something that we might expect not to work super well with some of the other catalysts that we have covered. And so the key question here is not necessarily what product is going to be formed, since this is the catalytic hydrogenation lecture and you've got some pi bonds, but to think through all different forms of selectivity here. You've got a chemoselectivity question. You've got two inequivalent types of pi bonds. You've got a stereoselectivity question. And what other selectivity questions do you have? Maybe just those. So selectivity is the name of the game here. That's the real question that we're asking about. Okay, Mike, what do we think here?
I think that like the ketone is like a lot easier to access, but I also think it could direct to, so like it still wouldn't be hydrogenated. 'Cause it's-
Direct. Okay, so let's talk about that nomenclature. So you said direct.
Yeah,
But what we're thinking about here is that if I understand you correctly, the lone pair from the ketone is going to form a dative interaction with iridium.
yeah, it'd probably be pretty weak, but probably the same as pyridine.
Okay, and then if you are able to generate your same dihydride intermediate, then what face of the olefin?
The top face, or the same face as the carbonyl.
So Crabtree's catalyst, because of its cationic nature, because of its weakly coordinating anions, because of its weakly coordinating pyridine ligand, has this increased proclivity towards directed reactions. In this case, Mike told us that the metal iridium dihydride is going to be directed to the top face. So delivering H2 from the same face of the ring as the ketone is disposed, which would push the methyl groups once to the bottom face. And you said that you preferred not hydrogenating the ketone, which I think is sound here. Any questions on that? Crabtree's catalyst is susceptible to some deactivation pathways that have been elucidated over the years. And this is what goes hand in hand with profound kinetic reactivity, is the possibility for deactivation. Is something I think Oliver asked an insightful question about this. Catalysts that are indefinitely stable ad infinitum often are not super reactive, and super reactive catalysts can be susceptible to deactivation. And so that's the case with Crabtree's catalyst. It can form these bridging hydride intermediates here, which then struggle to get on cycle. It can form these polymetallic metal clusters. And so you can imagine that because these are bimetallic deactivation pathways, one way to avoid this is running at lower catalyst concentration. So one of the ironies here is sometimes when we're trying to push a reaction, what do? We say, let's just increase the catalyst loading. But of course, that can, if you have a bimetallic or polymetallic deactivation pathway, that can actually have the nefarious effect of accelerating catalyst deactivation even more so than your on-cycle desired pathway. Okay, we'll talk about some other hydrogenation catalysts, which mechanistically are important to understand. As a practitioner, you'll probably encounter these less often, but it's important that we establish this framework because we're going to talk about related reactions that rely on some of these same complexes as we move forward in the class. So the theme here are catalysts that react via monohydride intermediates. And so one that to be familiar with, it kind of looks a little bit similar to if you squint to the Wilkinson catalyst design. And this is a rhodium tris triphenylphosphine monocarbonyl monohydride. And this can participate in hydrogenation, or this can promote hydrogenation of olefins, but through a slightly different mechanism than what we saw previously. Initially, it will, let's just do a quick electron count again. So we're situated here. You can never practice electron counting too much. Anna, what do you think?
This is your 1 plus,
Rhodium 1.
and then that's B6,
B6, okay,
and then that's 10 plus 6 is
16 electrons, okay. So in theory, then, this could bind an olefin directly to get to an 18 electron complex, but kinetically, the preferred pathway is initial loss of a ligand to get to this more reactive. And now this is going to be, is that 16 electron, Anna? Sorry. What did I do? What did I do wrong? All right, D8. So this should be what in terms of 18 electrons? Okay. So this gives us a hint of what needs to happen mechanistically. Is initial loss of a ligand to open up a coordination site, 16 electron. Now we can bind an olefin. Familiar looking steps here. Hydrometallation then gets to a rhodium alkyl intermediate that has a open coordination site. This is going to be trapped with an equivalent of H2, oxidative addition, reductive elimination. And so we've kind of, because one way to think about this is because we pre-install one equivalent of hydride into our starting complex. As this turns over, we only need to grab half of what H2 has to offer at a time per cycle. And so there's some kind of analogy here I'd have to think about. I'm probably going to say something and then realize it's an incorrect analogy, but there's some kind of connection here to like radical chain type processes. Don't quote me on that, please. Okay, so what, yes, Eugene.
Yeah, why doesn't the CO ligand do anything?
Okay, so then you can volunteer to think about what might happen here. What could go wrong? And why don't people use this complex instead of Crabtree's catalyst or instead of Wilkinson's catalyst? So one is that the scope is not that good. It only works for terminal olefins, so that makes it not super interesting compared to alternatives. But Eugene mentioned something that made him uncomfortable. This is terminal olefins, which is you've got this CO ligand present, and look what you have here. This looks pretty precarious. An alkyl group tethered to a CO. And why did this make you uncomfortable, Eugene?
You can get CO insertion maybe.
Aha. And then what types of byproducts might you expect to get out of this pathway?
maybe then you could coordinate your H2 and then just get the aldehyde out.
There you go. So what have you done overall in this process? We have added a H in an aldehyde, and we have done a hydroformylation, which is the topic of, one of the topics we cover in the next set of notes. See what I did there? So that is a common byproduct with this, but it's not the only byproduct. And so we can think about, it's always interesting to think about these different byproducts that can be formed. So what else might go wrong here? Anybody else uncomfortable, but for a different reason? Beta hydride. Oh, you want to do beta hydride and then what, Nathalie?
Flip back to them.
Got that open coordination site, you've got that tempting looking beta CH, and then you said you could go back, chain walk, okay. So maybe I'll draw this. On a different way then, and say chain walking is another, so alkene isomerization. And why this is problematic in this case is that this catalyst can only accept terminal olefins, not internal. So it will isomerize inward one position, and then it will not be able to do anything else with that catalyst. Sometimes the hydrogenation catalysts are so active that they're isomerizing, but they're reducing whatever that they get from isomerization anyway. So it's sort of a degenerate process that you miss. But in this case, it can only accept the terminal. So when it forms the internal, that's another dead end where you're going to consume starting material but not get desired product. Questions on that? Yeah.
So why do we use less than 1 ATM?
Why do we use less than one equivalent of H2? Why would you posit?
It's like, I think the pressure looks strange.
The pressure looks strange, but why would you think that that might be what's needed?
1 ATM is normal.
Is what?
I think 1 ATM is normal.
No, I know, but why, if I told you that this is what is needed for the reaction to turn over, how could you rationalize that?
Because we only need the 0.5 equivalent, 0.5 equal of hydrogen gas.
Well, you still need, yeah, that's kind of true, but you still, overall consume one equivalent of H2 for every equivalent of product that you make.
Yes, but yes, less than 1 ATM will make that explosive.
I would expect what might happen is you need reduced H2 pressure because you have another side reaction. You need to bind olefin. You need to have chemoselectivity for binding olefin here, not binding H2. And I think that you might form an undesired trihydride intermediate if you have too high of H2 pressure. Does that make sense? Okay, so where these monohydride intermediates, mono metal hydride intermediates and catalysts shine really is in carbonyl reductions. And so we'll talk about now different ways to reduce carbonyl compounds. And there's some kind of confusing nomenclature, or if it was me, if when I was a student, I found it confusing, is people will talk about a Noyori reduction to mean like 3 or 4 totally different kinds of reactions that have almost nothing to do with each other than the same guy invented them. Sometimes not the same ligand, sometimes not the same, everything different except the name Noyori. So you're going to hear a lot of Noyori reductions, and sometimes they're mechanistically quite distinct. So I'll try to make it as clear as I can. There are 2 big categories in general of Noyori classical hydrogenation, classical meaning that we use H2, and Noyori transfer hydrogenations. And those typically use isopropanol as the H2 donor and generate acetone as a byproduct. So this is a classical Noyori, but it's a carbonyl reducing Noyori. So what happens here is that this is also a substrate directed reaction. We get on cycle with this ruthenium monohydride. We've got a chiral bisphosphine ligand typically, and then we use 1 carbonyl to direct reduction of the second carbonyl. And so in this case, the more Lewis basic carbonyl, the ester is the director, and the more electrophilic carbonyl, the more delta plus carbonyl is the hydride acceptor. So it docks in the same bidentate coordination mode that you would see it with like an ACAC ligand, and now the more electrophilic ketone gets reduced from the intramolecularly tethered hydride ligand, generating a secondary metal alkoxide. Coordination of protic solvent, in this case methanol, then provides a means of protonating off the substrate to generate the chiral product. The regeneration of the hydride, reactive ruthenium hydride, then needs to happen, and that can happen via a mechanism of we can think, I'll leave this to you to think about the elementary steps involved here for generating the monohydride. But from what we've covered before, you can appreciate that there'll be some combination of oxidative addition and then reductive elimination or protonation. Yes, Eugene.
Is there like beyond ketones? I mean, does it work with like aldehydes as well, or like non-esters?
Yeah, so we'll talk about that. So I think if there almost any carbonyl imine, you can in the year 2025 find a way to reduce with some catalytic strategy, some metal catalyzed strategy. And I would say over time, transfer hydrogenation, which we'll cover in a moment, has gained more and more steam. And so that's where probably the lion's share of the effort. So I think aldehyde reductions are kind of less interesting to people because there are a lot of ways to reduce aldehydes and you don't form chiral products in that case, but there's been a lot of attention for ketones, ketamines, et cetera. Riku.
Oh, it's like a basic question, but then why can ruthenium hydrides reduce the carbonyl like that, but not for like the other metals we just talked about? That's just like a rhodium hydride.
Yeah, well, in this case, one of the factors is that it's directed. So you have induced intramolecularity that lowers the kinetic barrier. Yeah, that's a good question. I think a lot of olefin hydrogenation catalysts, both homogeneous and heterogeneous, if you push them hard enough, they will also reduce carbonyl compounds. So I think it could be a matter of chemoselectivity. Like the fact that I've shown it reducing the carbonyl here doesn't mean that it wouldn't reduce an olefin and wouldn't reduce that olefin in preference to the carbonyl, if that makes sense. Okay, here's a twist on this, just to keep things lively with some modern examples. Here's a case of a isomerization, but in an antioselective isomerization. So this can be thought of as a hydrogenation, but like a borrowing hydrogenation. That sometimes you hear that lingo, borrowing H2. So what's going to happen is in a 10,000 foot view, 30,000 foot view depiction, we're going to use the H2 equivalents of the secondary alcohol to reduce the tethered olefin. This is an example from Yu Zhao's group, and we use a familiar looking recipe here. So we've got rhodium biscod, cationic BF4 as a counter ion. We're going to generate our Schrock-Osborne type pre-catalyst in situ. Yu Zhao actually, who's at NUS, trained with Schrock. So this is like fourth generation of hydrogenation stuff. So let's take a look at the mechanistic details here. Some of the subtle parts I've just drawn out in advance because some of this you wouldn't necessarily be able to expect, but through the deuterium labeling experiments that they did in this paper, that they learned some things about this system. Okay, so we've got our active bisphosphine, rhodium 1, bis-solvato complex. First step is we coordinate the substrate in a bidentate fashion. And then what happens next here, Catherine?
So it's supposed to be a key.
I haven't drawn, nothing's happened yet. So this is, okay, so here, Catherine, we've got,
It's in the starting material.
Starting materials.
I see it. Okay, sorry about that. Is that better? Okay, so we've got a beta hydride elimination. Is that what you had in mind, Catherine? Okay, so that's gonna then shuttle our reducing equivalents from the secondary alcohol to the metal. The metal then shuttles that reducing equivalent to the olefin through a hydrometallation to make a chelated rhodocycle. The regioselectivity here is something that it's interesting to think through and do a thought experiment of why one versus the other. the authors did a labeling experiment, so they know the fate of that H atom. If you didn't know, you could maybe convince yourself that it's goes the way I have it drawn because it forms a benzylic metal species. And then there's another kind of chain walking beta hydride elimination process that takes place to generate an enone that is then reactive for a subsequent 1,4 conjugate addition. And these latter steps, I don't know that you'd necessarily, there's other sequences that you could draw that would be reasonable in the absence of additional information. So that's why I drew that out in advance. They know that this is the pathway based on the mechanistic experiments that they did, but you might not be able to think that just from a cursory glance at it. Okay, questions on that? Yes.
So it's the oxidation state of rhodium stays after the last, before the last, does the oxidation state of the last step stays constant?
What do you think? Is there any change on oxidation state of rhodium? Let's think through what are the elementary steps. You've got substrate, you've got a ligand exchange, you've got a beta hydride elimination, you've got a reinsertion or 1,2 microtorr insertion, another beta hydride elimination, another insertion, and then a protonation of the rhodium enolate. So all of those steps should be redox neutral at the metal. So if we track this down, we've got, should be rhodium 1 to start with, should be rhodium 1 here. We've got 1 alkoxide ligand, should be rhodium 1 here. We've got 1 hydride ligand, should be rhodium 1 here. We've got 1 alkyl ligand, should be rhodium 1 here. We've got 1 hydride ligand, should be rhodium 1 here. It's an alkyl. This is a C-bound enolate, but you could also draw the O-bound enolate version as we talked about. And then the last step is just a protonation, which is redox neutral at the metal as well. Good, questions? Okay, now we'll talk about this other flavor of hydrogenation that I alluded to, transfer hydrogenation. And often transfer hydrogenation, often but not always, involves a process of or a phenomenon of bifunctional catalysis, which is also referred to in the literature as metal ligand cooperativity. These are really beautiful catalytic systems because the ligand is working just as hard as the metal, and they're really working in harmony. And so it's a beautiful, they have a beautiful symbiotic relationship. So let's illustrate metal ligand cooperativity with a specific example, and that example is the complex shown here. Does anyone know the name of this bimetallic Schwo's catalyst? Do you know what this is used for, Adi?
I think it's for borrowing hydrogen shuttle or acceptor this hydrogen coupling. Different names for that thing.
So Madi said it's used for H2 shuttling, borrowing hydrogen, and also used commonly for isomerization. So you can take an enantiopure alcohol and then treat it with this catalyst and turn it into a racemic mixture. Why on earth would you want to do that? Well, you might want to do that in the context of a dynamic kinetic resolution, where you take a racemic mixture, you're constantly racemizing it, but you have a means, for example, a lipase, or you have a organic co-catalyst like the FUDMAP that can do stereoselective acylation. So you're always selecting out the R isomer and then you're replenishing the pool through an isomerization process. So this is a common isomerization catalyst, common racemization catalyst. For secondary alcohols in DKR systems, partnered with an enzyme or an organic co-catalyst. So how does the Schwo catalytic system work? It's really beautiful. This is the kind of thing you just dream to make this type of discovery, and you'd be hard pressed to ever design something like this. So in solution, it breaks apart into two components, an H2 donor component and an H2 acceptor. So it's one complex that associates into two non-equivalent catalysts that play different roles in an isomerization. So let's focus on what happens with the H2 donor when it sees a carbonyl compound. It's got what really is this chemical entity? It's a very unusual creature. It's a metal hydride, but it has tethered to it a proton. So it's got hydride and proton, i.e. H2 embedded across the ligand or distributed across the metal and the ligand. So when it's instructive sometimes to think about our partial charges. So it's partial plus at the proton equivalent and partial minus at the hydride equivalent. And then what can happen when it finds a carbonyl compound in the transition state, the hydride wants to go to the delta plus the carbonyl, the ketone, and the proton wants to go to the delta minus. And you see the metal is involved here, but in a different way than we saw before, where you might be tempted to draw this as a hydrometallation and then some kind of reductive elimination, but in practice, the agreed upon transition state structure now through a series of a whole number of experiments is the one shown here, where it's the metal and the ligand are cooperating to deliver an equivalent of H2. So where this is powerful, so of course, most of us, unless we're really focused on developing DKR type chemistry, we don't really have a strong desire for isomerizing enantiopure secondary alcohols. We prefer to make them. And so that can be done using the Naori toolkit of asymmetric transfer hydrogenation systems. And so the distinguishing feature of these Naori transfer hydrogenations is that they have this embedded, and I've tried to highlight it here, they have this embedded diamine system that contains a NH group. And so these are the pre-catalysts, and I'll allow you to think through, these are typically the pre-catalysts, and then they're activated through treatment with base, like KOH or something like that. I'll leave it to you to think about what happens when you treat these with base. But the active form of the catalyst then possesses something that looks very similar to what we saw in the Schwo system, where it can gain an hydride at the metal and gain a proton at the nitrogen, and then deliver to a ketone or to, this is what Eugene was asking about, or this could be, in imine here too. Also, this has been developed. Can deliver through metal ligand cooperativity an equivalent of proton and equivalent of hydride through a 6-membered transition state. Yes, Eugene.
How did these catalysts get regenerated? Because I can see the hydride going back to the metal, but maybe ligand is.
Great question. So it's this point, I have glossed over this. Where do I put this? Oh yeah, it's, so the overall, let me just draw this out here. So let's Thanks for bringing this up. So if we want to draw the overall reaction. And we need an equivalent of H2, right? So what we're gonna do is we're going to add an equivalent of isopropanol. And then the byproduct is gonna be an equivalent of acetone. So the catalyst grabs H2. So I don't have all the steps in the cycle drawn out, but we can just walk through this. So the catalyst is gonna grab H2. It's gonna accept a hydride on the metal. On the amine, it's gonna accept a proton. It's gonna grab that from isopropanol. Then it's gonna find your ketone of interest, your precious ketone. It's gonna deliver that equivalent of H2. So in the first step where it gathered H2, it generated acetone as a byproduct. Now you've generated your secondary alcohol. And now it can find another molecule of isopropanol, gather H2, make acetone, deliver H2 to the ketone of interest, and so on and so forth. So you might be wondering, and I think this is maybe the heart of your question, Eugene, which is, then surely all of this is just reversible, and I'm going to be in trouble. And that is a very, very important point, which is why you use very cheap, inexpensive donor alcohol like isopropanol. So through Le Chatelier's principle, you drive towards formation of the precious secondary alcohol that you care about. So you can use this as co-solvent, right? You can use 10,000 equivalents of isopropanol if you want. You don't care. It's so cheap. Yeah.
And so would that also be the reason why, that I imagine that cyclopropyl or the cyclopenta, whatever, that aromatic ligand, with the OH, I would imagine the pK of that alcohol wouldn't match up well against the isopropanol. Like that O- is probably more stable than the than the isopropanols O-.
It depends what you're reducing. So you're talking about if you.
In the Schwo catalyst,
Mhm.
OH on the ligand
Yeah,
probably has pretty low pK, right?
yes.
But isopropanol is probably higher than the O-.
Yes. So this has a relatively low pK, so that's acidic. Yeah. So what's your question?
Why is it the O- from the ligand that's grabbing the proton from the O of isopropanol, or what?
Oh, yeah, okay, so this is for the Schwo. Let's talk about the Schwo case. So we've talked about the H2 donor side, and then we can talk about the H2 acceptor side, and it's literally just it's the microscopic reverse of this transition state. So it's
Oh, I didn't think about the fact that there's an H2 acceptor. My bad.
do this very slow. But your point is so does this make sense for the Schwo?
Yeah.
Yes, yeah.
I just forgot that there's an acceptor, and I was thinking only about the donor. Yeah.
Yeah, and once the donor has delivered its H2, then it becomes an acceptor. So that's
Yeah.
the relationship that they have to each other. Okay, some of the common ligands that we see in hydrogenations, hydrogenations is really where the field of asymmetric catalysis got its start. We talked about the development of chiral at P ligands through the work of Mislow, or how the work of Mislow inspired the development of chiral at P ligands and how that got incorporated to DIPAMP and won Knowles the Nobel Prize. Another really important concept is C2 symmetry. C2 symmetric ligands don't necessarily need chiral information at phosphorus. They have chirality built into the backbone. So the first person to make great good use of this was Kagan, who developed this ligand diop, which if you look at it, you can see ultimately comes from tartaric acid. And it's always something interesting to think about is at the end of the day, all the chirality that we use on this planet, the chirality that's in drugs, the chirality that's in materials, it has to come from somewhere, and you can just keep pushing that upstream. So like, where do chiral centers come from? A lot of them come from hydrogenations, but then where does the chiral information in the chiral catalyst come from? It has to come from somewhere. So it typically will come from chiral pool at some point upstream, or come from a chiral pool material that's used in a resolution. It has to come from somewhere. I think it's like a soul, stirring, provocative notion to think where this comes from. So diop, the first version comes from tartaric acid. And then the beautiful ligand structure BINAP developed by Naori. I think now we all appreciate and to some extent take for granted what a beautiful contribution this is. It's an aesthetically pleasing molecule. The notion of using axial chirality as a ligand design, super novel and creative. That it really transformed the field of asymmetric catalysis. And then we can talk through, I won't go through these examples. I think they're probably useful to just think through on your own and draw out kind of the elementary steps, commercial applications of asymmetric hydrogenations in the Monsanto's synthesis of L-DOPA, Takasago. These are not hydrogenations, but isomerizations. You probably in classics, or in, I think the classics 1 textbook, they feature menthol synthesis, and similarly, citronellol synthesis from geraniol uses kind of similar principles, but is a little bit easier to illustrate this key point. And so nowadays, like, when you're doing your retrosynthesis and you're working in process, if you see secondary stereocenters, hydrogenation is a pretty good bet for a disconnection strategy. Okay, we're at 10:04. I'll just, I don't want to take too much of your time. I'll give a quick preview. We talked about carbonylation and how we probably weren't going to get to cover too much of it. I'll just give a quick preview of where we'll pick things up after the midterm. And I think Eugene set the stage really nicely with his question about, with these carbonyl ligands, why don't they get incorporated? Well, sometimes they do. We're going to talk about industrially important processes like the Monsanto acetic acid process. And we're going to talk about hydroformylation. And we're going to ground it all around sort of one of the key society defining reactions, which is known as the water gas shift reaction, where reliant there are H2 in the world that we use to make fertilizers, and the Haber-Bosch process comes from. So that's what you have to look forward to. Happy to stick around if you have any questions about the midterm or any other administrative questions. All right, if not, see you Thursday.